You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Juan Maldacena. Juan Maldacena is the Carl P. Feinberg Professor at the School of Natural Sciences at the Institute for Advanced Study. Professor Maldacena's work focuses on theoretical physics and specifically on quantum gravity, string theory, and quantum field theory. He has proposed a relationship between quantum gravity and quantum field theories that elucidates various aspects of both theories. He's studying this relationship further in order to understand the deep connection between black holes and quantum field theories. He is also exploring the connection between string theory and cosmology.
Dr. Juan Maldacena, welcome to the program.
Hello, how are you?
Now, Doctor, you recently wrote a paper about a very old subject that goes back to, well, Einstein and Rosen. The idea of a traversable, or at least the existence of a wormhole in the universe as we understand it. Now, your paper seems to center around a different sort of model than the standard model of the universe. This is the Randall-Sundrum model. What exactly is that model, and how is it different than the standard model?
Well, that's a model which originally postulated that you had an extra dimension. So you have the 4 dimensions that we see, and then there is an extra 5th dimension that is actually very large, but the space in the extra dimension is highly curved. It turns out that this model can be viewed alternatively as having our 4-dimensional space somehow coupled or interacting with a theory that has light or massless particles, a kind of dark sector that has massless or light particles.
Now, what creates the massively twisted nature of this 5th dimension?
Well, that's something that is postulated in this model, and there could be some more microscopic models, like let's say models with extra dimensions, such as in string theory and so on. In those models, there is some energy or maybe some magnetic type fluxes in the internal dimensions that could generate this type of negative curvature.
Within the standard model, there's always been a problem with wormholes that if they could exist, they collapse very rapidly. But in this other model, how are they held open?
Yeah, maybe I perhaps should start by reviewing a little bit the ideas around traversable wormholes, if that's okay.
By all means.
Yep. Yeah, so in general relativity, the geometry of space-time is curved and can have, in principle, different shapes. However, the shapes are constrained by the equations, and the equations roughly say that the average curvature of the geometry should equal the matter density. Now, in principle, one can imagine geometries that look quite weird, so quite strange. So you could have a geometry where you take 2 faraway regions in space-time and you cut out these regions and you somehow connect them to each other. And at the level of geometries, this is an allowed geometry. I mean, it's a possible geometry. There are some geometries that look a bit like this, that are solutions of Einstein's equations in the vacuum. Those geometries were found by Einstein and Rosen in the 1930s. And they look basically like 2 black holes from the outside. So from the outside, they look like 2 black holes. But if you go inside, they are connected. So the inside of these 2 black holes is common for both of them. So if someone jumps into one black hole and another person jumps into the other black hole, they can meet inside. So that's sometimes called the Einstein-Rosen wormhole or Einstein-Rosen bridge. It's a connection in space, but the solution is time-dependent. And as you evolve the solution in time, this interior region collapses, and inside it looks a bit like a big crunch. So a region where the space-time is collapsing and shrinking to nothing. And so if these 2 people who go into the interior, they can meet, but they will eventually die in this collapsing universe. So it's not a very happy place to go. And in fact, you can actually, so you can wonder whether there could be a solution where this doesn't happen, where somehow you have faraway regions, and then you can send a signal through this wormhole to a faraway place faster than the speed of light. This is a possibility that people have speculated a lot, especially science fiction writers and so on, because it would allow you to violate the principle of maximum speed. It will allow you to travel faster than the speed of light. But these geometries, in principle, you can think about, you can write them down. As geometries, they have nothing wrong, but they do not obey Einstein's equations with matter that obeys the standard principles that matter should obey. So classical matter obeys a certain positive energy condition, which forbids any kind of wormhole, so any kind of connection between two separate points, any kind of topology of a space-time with a little handle and so on. Those things are forbidden by just the Einstein equations and classical general relativity, and classical matter. Now, once you have quantum matter, the energy conditions are a little laxer, so you can sometimes have a little bit of negative energy. And people then returned to this question of traversable wormholes and wondered whether in quantum mechanics they would be allowed, whether once you consider quantum effects, maybe you could have those, perhaps those science fiction wormholes that allow you to travel faster than the speed of light. Now, people also did research on this question, and the conclusion is that these are still not allowed. So it's still not possible, even with the quantum effects, if those quantum effects are constrained by the laws of, let's say, quantum field theory and special relativity. Quantum field theory is a kind of theory that results from the union of quantum mechanics and special relativity. So the standard model of particle physics is a quantum field theory. And extensions of the standard model that people normally consider are also quantum field theories in this sense. And the energy can be negative, but not too negative, and in particular, not negative enough to allow traversable wormholes that would allow you to travel faster than the speed of light. So let me call those science fiction wormholes. So that's too bad, but in some sense it's too bad for science fiction writers, but in some sense it's good for the laws of physics, because general relativity is based on the idea that there is a limit for the speed of propagation of signals. And it would have been funny if these non-trivial topologies, which would be allowed, but if those non-trivial topologies were allowed, then general relativity itself would violate the principle that it was based on. So it would be a funny situation. But interestingly enough, this funny situation does not happen. And it doesn't happen thanks to an interesting interplay between properties of quantum matter and Einstein's equations. Now, what can happen is that you can have wormholes, traversable wormholes, but the time it takes you to traverse the wormhole, so to go through this non-trivial topology, so through this, you should imagine the wormhole as a little tunnel in space-time, where the tunnel has two entrances that are at some distance from each other. The tunnel is some geometry that connects the two. And so you enter in one mouth of the wormhole, and through this tunnel you come out in the other mouth of the wormhole. Now, an important question is how long it takes you to travel through this wormhole. So if the two mouths are at some distance, the wormholes that are forbidden are those that where the time it takes you to travel is shorter than the time it takes you to travel between the mouths in the outside space-time. So those are the science fiction wormholes. However, you can have wormholes where they have this geometry, but the time it takes you to travel from one mouth to the other through the wormhole is longer than the time it takes you to travel outside. So those are fine, and they're allowed. And in fact, you can find solutions that have these properties. And these were found very recently. They were based first on an idea by Gao, Jeffries, and Wald, who noticed that under certain circumstances, the quantum effects, or effects of quantum mechanics, can lead to negative energy that can make the original Einstein-Rosen wormhole. They can change it a little bit and make it slightly traversable. Then in subsequent papers with other people, well, including myself and others, we proposed with Milekhin and Popov, we proposed some solutions in 4 dimensions that use just the fields of the standard model. So just the physics of the standard model. With just that physics, you can construct a wormhole solution. It's just a solution, but it has this funny geometric shape of a wormhole. However, using purely the fields of the standard model, we could only construct solutions which are very, very small. So smaller than the smallest distances we can see together. We can see today with our best microscopes. The best microscope is the Large Hadron Collider. And they involve also things like magnetic monopoles and things like that. Well, not magnetic monopoles itself, but magnetically charged black holes, which would be very difficult to produce in the standard model. I mean, they're in principle possible, but very difficult to produce. So those are some solutions. And then we were wondering that the paper you mentioned came out of thinking about whether these solutions could be possible if we assume certain properties about new physics, so physics that we haven't yet seen. So the question is, could the laws of physics be such that we could have bigger traversable wormholes that are big enough, in particular whether they could be big enough for a person to go through? The answer was that it is possible if you assume a certain dark sector. So by dark sector is set of particles or part of physics that does not interact directly with the known physics, with the standard model, through standard model interactions. And so if the dark sector is of this particular Randall-Sundrum type that we mentioned before, then it is possible to find traversable wormholes which are big enough for a person to go through. So that's basically some of the background. So I tried to summarize some of the background for this paper and what this paper was doing.
In the paper, you mentioned that the wormhole, under this specific condition, under these assumptions, the wormhole must still be very clean or it collapses. So if you have particles entering it, you're going to have to make sure that those aren't there, right?
Yeah. Let me discuss a little bit more the geometry of this wormhole. They have an interesting property. So as I said before, they are kind of like a tunnel. And I said before that the time it takes you to travel through the wormhole is longer than the time it takes you outside. But it is only longer for the person who stays outside. For the person who travels through the wormhole, this time is very short. This is possible thanks to the fact that it's possible due to 2 effects. First, there is a large so-called gravitational redshift. So that means to say that the time inside the wormhole runs very slowly. Second, there is sort of like a large gravitational potential that pushes a traveler, gives a very large speed to the traveler when this person travels along the wormhole. So these 2 effects together, they give rise to a kind of time dilation effect that implies that the time as felt by the traveler himself or herself is much shorter than the time that an outside person measures. It's roughly similar. It's very similar to the issue of the twin paradox, right? So let me just remind you of the twin paradox. So in the twin paradox, you have 2 twins that are born at the same time, and one remains at rest, and the other travels with very high speed far away and then returns. The twin that returns is much younger than the twin that stayed at rest. And so the twin that travels is younger because it was traveling at high velocities. Here we have a similar effect. The person who travels through the wormhole, if we had 2 twins and one travels outside the wormhole and the other travels through the wormhole, the 2 would meet. The one that travels outside will reach the other mouth of the wormhole earlier. But once finally the twin that goes through the wormhole emerges from the wormhole, that twin would be much younger than the previous one.
So in other words, the twin going through the wormhole passes through the wormhole momentarily, but if you're going from, in the normal universe, from one end of the wormhole to the other, it takes thousands and thousands of years.
Right.
So that it's all, once again, relative perspectives.
Yeah, that's right. So with particular parameters, we gave an example in the paper where you could have wormhole where the distance between the 2 mouths of the wormhole would be roughly like 10,000 years. So the time to go through the wormhole as seen from the outside would be longer than that. But the time going through the wormhole would be like 1 second. So it's a very, very drastic example. And it is something that, in theory, you would be able to survive traveling through this wormhole. So you are accelerated with very high speeds. And if the wormhole is very clean, as you were saying before, then you can do that. But if there is a little speck of dust that enters through the other mouth of the wormhole and it hits you, then you're dead. So it's dangerous.
So always keep everything clean inside this. Now, are there limits? So say you can create a wormhole like this. Is there any distance limit in the universe to where it's just simply too far, or could you just literally go anywhere in the observable or inobservable universe? Is there some sort of limit as to, how much can you twist this geometry?
Right. Yeah. If you were, in principle there are limits. I guess if we were in flat space, in empty flat space, and you take it really very, very far, then the effect of the negative energy is not strong enough to keep it open. So that's one limit. Now, there are more practical limits in our universe, which is that even if you somehow could make this geometry, just the fact that there is a cosmic microwave radiation that could enter this wormhole, that radiation would accumulate inside and eventually also make it close or prevent the traveler from traveling through without dying. There is also the fact that this extra dimension we were talking about would get heated up by some of the heat in our universe. So these are all issues that make it impractical today. So by today, I mean this time in the evolution of the universe. Maybe even in the very far future, it might be possible. But even all of that is assuming that there is a dark sector and there are some laws of physics which allow these wormholes. Something I should emphasize is that this type of dark sector and so on was considered before, and it's consistent with all the principles of special and general relativity and quantum mechanics, special relativity and quantum mechanics. So you could view it as a type of quantum field theory. So it's consistent with the laws of physics, with the very general principles of physics. It's not somehow consistent with the standard model and gravity, but it is consistent with general principles of physics. So that we had to invoke some extra unseen matter to find the solutions. So it's just I think I would view it just as a curiosity of what is vaguely possible. But you should not expect that you will be able to make them or find them in our own universe anytime soon.
Now, that leads to a question. There's always been floating around the discussion regarding wormholes. There's always been this concept that you would need some kind of negative mass or exotic matter or something like that to even begin to think about creating one of these things that could be traversable. Is that also applicable to a wormhole in this Randall-Sundrum model?
No. So when people talk about exotic matter in the context of wormholes, what they mean is matter that has a very relatively large negative energy. And it's a kind of negative energy which we think is not allowed by the very general principles of special relativity and quantum mechanics. So it's not that it's not allowed by the matter we find experimentally in our own universe, by the matter of the standard model, but it's also not allowed by the matter of most extensions of the standard model that people normally think about. So it's, in the history of physics, in the 20th century, there were some principles that were laid out, like quantum mechanics and special relativity and general relativity, that have held on till today. The particular matter content has not. I mean, in the beginning of the 20th century, there were only electrons and protons, neutrons, and many new particles were discovered. All these new particles that were discovered, they all obey these general principles of quantum field theory, which is just the word we use to describe theories that are joining together special relativity and quantum mechanics.
Now, early in the discussion, we covered that these would look like black holes, right? Even in this sort of...
the Einstein-Rosen ones, they would look like black holes.
What would these...
And so these ones would look somewhat... to discuss what this look like, I need to discuss a type of black hole first. which are the so-called charged black holes. These are black holes that carry some charge, so it could be some magnetic charge, for example. And then such black holes have to have a mass bigger than a certain threshold that depends on the mass, on the charge, sorry. And when they have the minimum possible mass, they develop a very long throat, a very long neck, let's say. And then the horizon is at the bottom of this neck. You should imagine them as a kind of big gravitational well, like a very deep well. And at the bottom of the well, you have the horizon. So that's how these black holes look like. Now, the wormholes we were talking about, they start, let's say, looking similar to two black holes like this. But if you go in instead of finding the horizon and the interior geometry and so on, what happens is that these long potential wells are just simply connected to each other before they encounter the horizon. So the final geometry has no horizon. And that's what allows a person who's traveling to go in and then come out again on the other side. So that's roughly how they look like.
Now, traveling through the wormhole, say we're in a spacecraft going through it, this stable, traversable wormhole.
Yeah.
It would just be instantaneous, right? You would enter and then come out the other side, again, relative to your position inside the wormhole, regardless of how much time has passed in the universe, or the normal universe anyway. Now, this makes this like any other sort of conceptual idea of wormholes. It makes it a time machine. You're traveling into the future by going through the wormhole, correct?
Yeah, you're traveling to the future in the same sense that in the twin paradox, one of the twins is traveling to the future. So he's younger than the others when he gets to the end point.
So that in itself sort of resembles a black hole interior, right? As you pass the event horizon of the black hole, you are looking down at the future as you approach the singularity. And therefore you must go towards the singularity because it's in your future. Is that the same with the wormhole? Is there a point of no return where you can't actually stop yourself from going through the wormhole? No, there is no such thing for a wormhole. So this collapsing universe that is inside the black hole interior is only a property of the black hole. So when there is a horizon and so on. In the case of the wormhole, you can at any point decide to do something different. And you will travel through the wormhole, but the main difference between the two is that in the black hole, if you go in, you die, and the wormhole, you go in and you come out the other side and you don't die. But you are in the future, so you can't ever go back to the past. You're still...
No, you cannot go back. So general relativity and so on, it allows you to travel to the future. So you can travel to the future faster. I mean, we're constantly traveling to the future, right? At a certain, let's say, speed, at the speed that our clock ticks. And it is possible to go faster by moving very rapidly, like in the example of the twins, or going through those wormholes and so on. Being in the presence of a high gravitational field, you also travel to the future faster. And that's allowed. What's not allowed is to travel to the past, or to travel at speeds larger than the speed of light. So those are the things that are not allowed.
But this doesn't violate that. You're not going faster than the speed of light.
No, this doesn't violate that, no.
So you are still, it is consistent with everything else in the universe in that you cannot go faster than light, you cannot go backwards in time, but you go forwards, and by going forwards, you can end up at a certain point. Now, with this wormhole, say someone is actually traversing it, and you are an observer on the outside. Could you actually see the person traveling across space, or would they be invisible in some other higher dimension or something like that? I mean, could you actually watch their progress across the universe?
No, basically you cannot watch them. It's like imagine two big wells, and you see someone going into one well and comes out of the other well, right? But you don't see how the wells are connected. In a certain sense, it's somewhat similar to a wormhole as the holes that worms make, right? Imagine an actual wormhole. So you have the surface of the ground, and there is one entrance of the wormhole and another, right? And it's somewhat similar to that.
Now, with this sort of model of multidimensional space, which is something that keeps coming up, whether it's string theory or whatever model you want, you are essentially traveling through another dimension, more or less. You're sort of taking a shortcut through a very convoluted, warped area of space-time that we can't see.
Mm-hmm.
Is that the right way to visualize it?
Yeah, the particular solutions that we discussed, you can think about them that way. Yes. It looks, you could imagine that there is a fifth dimension with, let's say, something like a constant gravitational field. And then you have this little tunnel similar to an actual wormhole that goes through the extra fifth dimension. So that's one point of view, and it's perfectly valid point of view. There is also, the most interesting aspect of this is perhaps not this, but something that might be a little hard to appreciate. But the interesting point is that there is another point of view where you can replace this extra dimension by some matter fields, some matter that lives in the original four-dimensional space. And in this point of view, what happens as you go through this wormhole is very interesting. But perhaps before I discuss it in more detail, I'd like to explain a little bit more about black holes, because it's important to have this picture of black holes. So far we discussed the black hole as geometry, as a space-time geometry, and that's the description we have in general relativity. However, once you start thinking about general relativity and quantum mechanics, you are led to thinking about black holes in a slightly different way, as thinking of the black hole as being some object that obeys the laws of quantum mechanics with some finite number of degrees of freedom. So you can view it as a, let's say, very complicated atom with huge number of very complicated material, let's say. And from that point of view, when a person falls into a black hole, what happens is that it goes and interacts with this material, and it gets destroyed by the dynamics with this material. It's like jumping in a pool of acid where you get completely dissolved. And so that's the picture of the quantum mechanical picture of black holes. So in this picture, the traversable wormhole would look like the two black holes would be entangled with each other. So you have some fluid, let's say this acid we were talking about, and the particular quantum states of this acid is completely entangled between the two pools. Let's say the two pools of acid, two droplets, are like the two black holes. And then when the traveler goes into one of these pools of acid, gets dissolved, and then there is a kind of quantum fluctuations or radiation that travels through particles in the embedded space-time, goes into the other pool of acid, and causes the person to reassemble in the other pool of acid and emerge from the pool of acid. So it's something that looks very strange, but that's the picture you get. And you can understand this picture in quantum mechanical terms as a version of quantum teleportation. So quantum teleportation is some phenomenon that can exist when you have entanglement. And in this case, you have the entanglement between these two black holes. And so you can view this as an example of quantum teleportation. And it was really by thinking about these examples of quantum teleportation and so on that all these recent examples of traversable wormholes came about.
But there's a difference between this and traveling through a wormhole, because quantum teleportation, you're essentially being deconstructed and then reconstructed, whereas through the wormhole, you're not, right?
That's right. So the difference is in how you feel. But what we claim is that it is the same. So we claim these two pictures are the same, but certainly you feel, certainly with this kind of teleportation, you never feel bad. You never feel that you died or anything. So in some other kinds of teleportation, the person would feel that he or she dies, but then he or she is reconstructed on the other side with all the memories intact and so on, and having forgotten that he or she felt that they died. So that's the difference between the two.
I see.
Yeah, but I think the interesting point is that in these cases, the idea is that you could have this very mild type of teleportation where you don't feel anything special when you are being teleported, and that's surprising.
That could have implications on things like communications and non-animate matter. So you could send supplies to someone, or you could communicate to someone, but you're still beholden to the speed of light limit.
Yeah, the speed of light limit. You could use it for that. You could use that. You could use it for that, but I have to say that if you want some practical use, there are more practical ways of communicating. So, but one feature that this type of communication has is that it's very secure. So people had discussed quantum teleportation in the context of secure communication. And so there, the laws of quantum mechanics somehow forbid anyone from eavesdropping on the communication. Here, this security is due to the fact that the message is somehow passing through this wormhole that is not accessible to the observer that stays outside, or at least not very easily accessible. It's related to the question you asked me before of what the person outside would see. So they would not really see you traveling through the wormhole very easily. Or to first approximation, let's say they would not see you travel through the wormhole. And for that reason, the communication is secure. This is related to the security of the communication.
Yes, and I can't imagine that anyone could ever come up with a way to break that sort of level of security, that where your communication is inside of a wormhole traveling through another dimension.
It would be very difficult to break, but it's also very difficult to produce this kind of entanglement. So it's not that we're going to see it anytime soon, I think.
Communicating in that way would probably, even given the security, not be worth it.
Probably not, yeah. The reason we're thinking about this is more to learn about the features of space-time. So to learn, just by knowing that this is possible in space-time, we are kind of seeing the kind of tricks that space-time can do. Quantum mechanical, the interrelation between quantum mechanics and space-time can do all these various tricks. And I think this will teach us something about space-time.
Now, my last question for you is in regards to a quantum mechanical version of this, a very, very tiny one, of this type of a black hole. Is there any way we could study that and see if these sorts of things are present in nature? I mean, can we get down to some sort of a scale, since this can be bigger, more than anything that's usually thought of as a wormhole in quantum mechanics? Would this be easier to study and look for if these happen in nature than, say, a standard model wormhole?
These objects are difficult to produce, I think, and we haven't come up with a simple way of producing them. But by simple, I mean even possible within the lifetime of the universe or something like this. So we found them as solutions, but we don't know whether they are simple to produce. And so, I mean, even some of the ingredients are a bit exotic. So even for the standard model black holes, the wormholes that arise in the standard model, they involve these magnetically charged black holes, which themselves are not terribly easy to produce, but are at least there are some scenarios where maybe there could exist. So they haven't been detected yet, but it is certainly something that could in principle exist. But then you would have to bring two such magnetically charged black holes and bring them relatively close to each other and wait for a long time for the wormhole to form. And we don't know exactly how long you should wait for the wormhole to form. I don't know if this answers your question.
Fascinating stuff. Well, thank you for joining us today, Doctor. I hope you'll come back sometime when you release another paper, and maybe it will become easier with time figuring out whether if we could ever create a wormhole or not. But it definitely is interesting, especially in regards to understanding space-time.
Sure, it's a pleasure talking to you.
John, are you aware that the opossum has a name for you?
No, I don't speak possum. I can't understand a word he says. What is this name?
He calls you Schrodinger's human.
What? He's the one that came out of a box, not me.
From his perspective, you are the one that came out of a box. And knowing you, it was probably a cheap box.
I remember that differently. Quantum mechanics is confusing.
Well, I suppose there has to be at least some differences between the two of you.
Yeah, well, one is that I'm not a quantum mechanical possum, Anna. Yeah, and on that note, next week we'll be joined by two greats of speculative science fiction. Awards galore here, folks. It is Gregory Benford and Larry Niven. See you then.